Good morning and welcome to Advent of Code in F#, day 13 already. That means we passed the halfway point. Good on us. Now, before we dive into today's video or today's puzzle, I wanted to quickly come back to day 12 because when we were solving that puzzle, I shortly mentioned something called property-based testing, and I went and had some fun with it yesterday, which I wanted to share with you. So if you've been following along, I use like these kinds of automated tests a lot when I'm playing around, or not a lot, but when I do use tests, I use these kinds of tests. And there's another style of testing, like called property-based testing, which I wanted to do a quick demo of. There's a really great introduction to it on F# for Fun and Profit, the site I showed a while ago. I'll put a link in the description. So this is like the best introduction I've found on the topic. But anyway, what is this property-based testing beast? In F#, I use fscheck, but there's others, but this is the one I found most documentation about. And I wrote a bit of plumbing, so it doesn't get in the way for us. But what actually is it? It's a different style of writing a test. So compared to the usual style where I like give a concrete example, for example here I say like if I rotate my waypoint from the ship puzzle yesterday, if I rotate it right by 270 degrees and this is where the waypoint is at right now, it should end up here. So these are like concrete examples. Property-based testing like takes another approach and lets you specify invariants. So for example here I say like if you rotate for 180 degrees to the left, that should result in the same result as rotating 180 degrees to the right for 180. Yeah. So this is literally stating that like invariant. And then I just give it to the property-based testing library, and it'll try to break this invariant. So it'll generate a lot of random inputs. So if you look at my property, the input is this. A coordinate is a pair of integers, so it will just generate like a whole lot of, I think it's like 100 pairs, but you can like go crazy and do 1,000, 10,000, whatever. But it'll generate random data and it'll try to run your code and it'll check if this property holds. And if it holds, it's like quiet. So for example, this is correct, so it's passing. But if I introduce a bug somewhere, or like for example, let's have so imagine this is a bug in my rotate waypoint, so this is obviously not correct, but then the quick check library or the property-based testing library is going to crash and say, hold on a minute, like there's a problem with your property, and it even like gives the coordinate or like the randomly generated input where things go wrong, so then you can start debugging and stuff like that. So I find property-based testing a really nice and a complementary way actually of testing. So for like concrete examples, I do this, but the properties are there to think up cases you didn't even think of, like edge cases or like special cases. So it's a really fun tool to have in your bat belt. That being said, let's go take a look at day 13. Where is my Advent of Code? Where is my Advent of Code? There we go. Day 13 is up there. Shuttle Search. Our ferry can make it safely to a nearby port. Oh, we're almost on our holiday destination, but it won't get much further. When you call to book another ship, you discover that no ships embark from that port to your vacation island. Okay, we're stuck. We'll need to get from the port to the nearest airport. Cool, so we're going to use a shuttle bus service to bring us from the seaport to the airport. Each bus has an ID number that also indicates how often the bus leaves for the airport. How often? Okay, so the bus ID is how often the bus leaves for the airport. Cool. Schedules are defined based on a timestamp that measures the number of minutes since some fixed reference point in the past. Sorry. At timestamp 0, every bus simultaneously departed from the seaport. After that, each bus travels to the airport, then various other locations, and finally returns to the seaport to repeat its journey forever. So we have infinitely driving buses. The time this loop takes a particular bus is also its ID number. Okay, so that's easy. The bus with ID 5 departs from the seaport at timestamps 0, 5, 10, 15. Okay. This reminds me of puzzles of previous years. Okay. The bus with ID 11 departs every 11 minutes. If you are there when the bus departs, you can ride that bus to the airport. Yay! So our input consists of 2 lines. The first line is your estimate of the earliest timestamp you could depart on a bus. Okay. The second line lists the bus IDs that are in service according to the shuttle company. Entries that show X must be out of service, so you decide to ignore them. That's part 2. That's a hidden part 2 right there. Let's take a look at what we're talking about here. Let's grab it. Let's put it into a... I'm like making weird head noises because my microphone is right here in front of me. And it's like hiding my keyboard a bit. This is a rather interesting input. So we have an estimate of the first second we can leave. Yeah. The second line are the bus IDs. So every bus ID is also at which tick a bus leaves, and we ignore the X's because that's part 2. Okay. To save time once we arrive, our goal is to figure out the earliest bus we can take to the airport. And there's exactly 1 such bus. Okay. So let's start with a small example, always a good idea. So we can depart at the earliest at 9:39. And the bus IDs in service are blah 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 blah. And then we look at what's the earliest bus we can use after 9:39 or on or after 9:39, and these are like the moments they're available. Yeah, sure. So 9:39 is here, and the earliest bus would be bus 59, right? Yes. And it doesn't depart until 9:44. That is correct. So we need to wait a while. Yes, that makes sense. And the while is just the difference between those 2 timestamps. Yeah. Multiplying the bus ID by the number of minutes, you'd need to wait. Okay, but that's a detail of how we give our submission. So our first thing we need to do is find the earliest bus we can take to the airport. Okay. Should we leave the input as is? Yeah, let's leave the input as is. There we go. Yeah, let's write a parsing function. We've been doing it forever now. What do we need? We need for part 1 at least, we need our timestamp and the bus IDs that are not X. So timestamp is just the first line, and let's parse that to a long, because I have the feeling that the numbers might be big today. And for the rest, let's make this a sequence of strings so our compiler can help us. And let the bus IDs be sure. Let's take the second line. Let's split it. Split it on a comma. It's comma separated. Yes, it is. And let's ignore the Let's ignore the X's. And let's parse, yeah sure, let's parse the bus ID map to an int 64 as well. And our parse should return both, so let's not go too crazy on the types today and just return the timestamp or our earliest convenience, and let's return the bus IDs as a list, why not? Where's my end key? There we go. No, that's not the end I was looking for. Oh, and apparently if I split a string, it ends up in strings, not in characters. That makes more sense actually. Okay, let's just format this a teensy bit because it ended up being way more steps than I thought. Okay, there we go. Let's try it out. Yes, and 1941, there we go. And our end bus, or the final bus on our list, should be 23. That appears to be correct. Okay, so now we parsed everything we need. Everything is along, so we can make really nice and big numbers. Cool. Now, strategy. So, starting from this timestamp, we need to figure out which of these buses will appear first. I've got a feeling that we might be will be hitting like performance problems. Wait, let's see. Those numbers are actually not too bad. No, that's actually not too bad. So we need like the multiples of every number, but we don't need to start at the beginning. We can just start like from here and look like what the next multiple of a bus ID is and take it from there, right? Or we could do like the naive approach and like just generate like for bus 19, let's generate every timestamp where bus 19 enters. That's also valid. Maybe that's a cool way of doing it. Let's go purely functional, lazy lists. Let's go all the way. So we need to have a, or what's the strategy I'm thinking about? For every bus ID, like let's generate an infinite list of numbers representing like all the timestamps where this bus, when this bus arrives at our seaport or where we're starting point. So, for example, for 19, is there a helper function we can use? Yes, there's this thing called Initialize Infinite, and that thing generates an infinite sequence. And you provide a function, like an initializer function, and that takes, I think it's the index, and it returns like the next element in the sequence. So if we try to generate an infinite sequence, and this is a function that takes the index, let's for example use just like generate a sequence from 0 to like infinity. I think this could help us. So this generates a sequence from 0 to infinity. But if we do something more interesting with the index, we end up with something more interesting. So I think if we do like index times the bus ID, so in our example 19L, and let's make the index in 64 as well, so multiplication will work. Good enough. And let's skip the 0. I think like this is the sequence for bus ID 19. So it'll first appear on the 19th tick and then on the 38th, and there we go. So let's wrap this into a function. Yeah, let's write this into a function. Arrivals for the bus ID, for example. And the 19 we hardcode in here is actually our bus ID. So timestamp bus IDs is this. That was a expensive save operation for some reason. Okay, there we go. Now let's map every bus ID we have to the infinite list of arrivals. So these are all the arrival times for every bus. And what do we need to find? We need to find the earliest bus arriving after our timestamp. What's the best way to do this? I'm thinking from this timestamp on, so from 101 whoop. Maybe starting from like the first tick wasn't that smart. I'm like debating whether we should, for every bus, figure out the index in the arrival times, but that could take a very long time for a small. That could take like infinitely long if one of these buses never gets there, but actually they all get there because they always increase in numbers. So eventually they will end up past this timestamp. It's not the fastest, it's not the best algorithm for today, but I'm guessing it'll work. So my strategy will be, for every bus ID, find like the earliest, or the index of the earliest timestamp that's bigger than the timestamp that we're ready, and like the smallest index of those will be the bus that wins, basically, the bus we get on. So we need that bus's ID, yep. And we need the number of minutes we'll need to wait. So we need the actual number as well. Yes, that's also possible. Okay, I think that'll work. So for every arrival time, let's look at what's the index of the first arrival time that's like we're ready for it. So if you use a find, I think it'll stop at the first time the predicate you provided is like evaluates to true, and because every bus will eventually be ready, it might not be the earliest, but every bus will hit the okay, we'll at one point be able to get on it. I think we can do this. So for every bus, find the timestamp that is bigger or equal to our timestamp, and let's call this arrival. So the bus's arrival, should be after our timestamp. Yep. So for every bus, try to find the earliest arrival after when we're ready. Yep. Cool. And can we grab the index? How do you do that? So let's provide the index and let's do min by the value. So it's our 6th bus in the list. So bus IDs. So earliest bus index is 6. Now it's actually 6. And right, what did we need? So sorry, that's not the earliest bus ID, it's the earliest bus index, and the earliest bus ID is the bus IDs and get me the 6th. So this is my earliest bus. It's bus 643. Is that a bus in my input? Yeah, it's a bus in my input. Cool. What did we need to provide for port 1? So it's our bus ID multiplied by the number of minutes we'll have to wait. And that was the second part of this tuple. Yeah. So let's do this. That's the same. And this is the bus's arrival time. So let's do wait time. Let's do wait time. Is the earliest bus, and it's the value, and minus our first time already, which is 5, and we need to do 5 times the bus ID, wait time times the bus ID. There we go. This should be part 1. And if it's not, we can look at the example again. But it is. Cool. Fun little number puzzle. I get the feeling we're gonna burn some CPU cycles again for part 2. But first, coffee. Refreshing. Hello, this is a message from the future again, because part 2 proved to be a bit more tricky than I expected. If you don't want any spoilers for Advent of Code Day 13 part 2, then I suggest you click away now. Okay, everyone gone? Great. What the hell? What the hell was this puzzle? I spent, I think, 4 hours today noodling around and trying to remain spoiler free, and I got as far like with optimizing and writing my book full with notes. I don't know if you can see this, but I have like diagrams for every test case we get in the day solution, and eventually I ended up with something that worked for every test input we got. So let's drop down to the screen. Yeah, so I ended up with something that worked for every given example, but it was still like untractable for my input. Now I was getting depressed, so I stopped and I looked for a hint on Twitterverse, and I found a hint. Let me just mention Tartan Llama Cybrand. Yeah, let me just mention the source. There we go. This kind of helped me. So this is the major spoiler. You have to use this Chinese remainder theorem to solve this problem with a reasonably priced computer. And it turns out that like my attempt, like my spoiler-free attempt, I was doing the Chinese remainder theorem. I was doing it, but I was doing like the naive version of it, and that was not fast enough for the big input. So actually I'm really bummed, because I like ended up at the solution, but my solution was not a fast variant of the algorithm. So this is just me spoiling part 2 for you, explaining that yes, you need the Chinese remainder theorem, and no, you do not. You cannot use like the basic, just try every number and do the modulus. No, you really need like the fast or the sieved version from the theorem. And I'm not even going to explain it because I understand what's happening, but I understand it because I watched a YouTube video. So I will be providing a YouTube video for people that want to do it on their own. It was this, it was this video by Maths with J, and she really explains how to do the fast algorithm for the Chinese remainder theorem. And then you end up with a huge number within seconds, or within, it's not even within seconds, it's like almost instantaneously. It's like, and there we go. And that's day 13. So yeah, I'm really bummed. I'm proud of myself for like getting to the correct algorithm, but I'm a bit bummed because you needed like some obscure mathematical knowledge to finish part 2 today. So you win some, you lose some. I'm really happy I found the spoiler online because I think I would have lost my mind otherwise. I hope this was the first and only obscure mathematical theorem challenge we see this year. And hopefully see you tomorrow. Bye.